This is lesson 5.3, multiplying polynomials. Our learning objectives are to multiply monomials together, multiply a monomial by a polynomial, multiply a binomial by a binomial, multiply a polynomial by a polynomial, multiply special products, and multiply polynomial functions. All right, looking back at section 5.1, as we began chapter 5, we learned how to add and subtract polynomials. Now we'll multiply them. Here's a quick little review for you. Here's back to section 5.1, where we added and subtracted polynomials. And we defined what a polynomial is. It's an algebraic expression with one or more terms combined with addition or subtraction. So a monomial is a polynomial with one term. A binomial is a polynomial with two terms. A trinomial is a polynomial with three terms. And this keeps going actually as far as you want to. You could have as many terms as you would like in a polynomial. Now, we need to get you comfortable. My goal is to get you comfortable multiplying a monomial by a monomial, or a monomial by a binomial, or a monomial by a trinomial, or a binomial by a binomial, or a binomial by a trinomial. This is my goal, is to mix it up so that you could do any of this. So let's begin talking about example 5.25, which is multiplying two monomials together. So here's a monomial multiplied by another monomial. And so let's go ahead and dig into how to do that. Now, when I see 3x squared times negative 4x cubed, I like to rewrite things. Since this is all multiplication, I could take 3 and multiply it by negative 4 and multiply that by x squared and multiply that with x cubed. So multiplication is commutative, and there are four things being multiplied together technically, and so I can reorganize that how I want to. You can do the same thing. And why is that good? Because I could take 3 and multiply it with negative 4 and get the new coefficient of negative 12. And then we can use the exponent rules that we've talked about in the previous lesson, like x squared times x cubed, and we can turn that into x to the 2 plus 3. We said the product rule says we can add the exponents together. Okay, so there we go. If you need a little extra practice with your exponent rules, please go back to lesson 5.2, the previous lesson before this one. So we have just multiplied two monomials together and simplified this to get negative 12 times x to the fifth. Let's look at another. The goal is to practice this. I see negative 5, 6 times x cubed times y times 12 times x times y squared. And I can reorganize this stuff how I want to again. I could take negative 5, 6, multiply it with 12, multiply that with x cubed, multiply that with x, multiply that with y, and multiply that with y squared. I still have all the same pieces, but I've multiplied them in the order that I like to, because I wanted to group all of my coefficient numerical values together, my x variable terms and my y variable terms, because now it'll make sense what I'm going to do to finish this. I'm going to multiply negative 5, 6 times 12, and that will give me negative 10. And then I'm going to multiply x cubed with x to the first, and that will give me x to the 3 plus 1. When I multiply like bases, I can add their exponents. Okay, so 3 plus 1, that gives me 4 as the exponent for x. And then I can take y to the first times y squared and turn that into y to the 1 plus 2, which is y cubed. 1 plus 2 is 3. Now I have multiplied these two monomials together into one single monomial. Great. So we just practiced multiplying a monomial by a monomial. Well, let's now practice multiplying a monomial by something larger, like a binomial or a trinomial. Okay? So what if I encounter this situation in example 5.26, where I take this monomial and I multiply it with a trinomial? Well, I will have to multiply the term of the monomial with every term of the trinomial. So you could think of using the distributive property. That's what's being used here. And so I'm multiplying negative 2 times 4 to get negative 8. and then y times y squared to give me y cubed. And now I move on to the multiplication of the monomial by the second term of the trinomial. So negative 2y times positive 3y. Well, negative 2 times 3 is negative 6, and y times y is y squared. And now I'm going to distribute negative 2y and multiply it with negative 5. And negative 2 times negative 5 is positive 10. And then I still have that y. Okay, so I have now multiplied a monomial by a trinomial, and I got this result when I did it. Let's practice doing this again with this next example. Here I'm going to take 3x cubed y. That is my monomial. It's a mathematical expression with one term, and I'm going to distribute it to all three of the terms of this trinomial. We're going to multiply this single term with these three terms, one at a time. All right? So when I see this, I jump into it and I say, well, I've got 3 and x cubed times x squared gives me x to the 3 plus 2. I'm adding the exponents together. 3 plus 2 gives me an exponent of 5. And I still have the y, right? So I had the 3 coefficient. There was no other coefficient here. I see x cubed times x squared. I got x to the 5th. And I see this y. It's still there. Let's move on. We're going to multiply this, this first term in front by this second term of the trinomial. Ready? 3 times negative 8 gives me negative 24. And x cubed times x gives me x to the 4th. Because remember, this is x cubed times x to the first power. There's a first power. 3 plus 1 is 4 for the exponent. And now thinking about y to the first times y to the first, y times y, that's y squared. And now moving on to the last term of the trinomial, this y squared here. So this y squared will multiply with this y to make y cubed. Y times y squared is y cubed. And so I can write this as 3x cubed y cubed. So I had the 3 and the x cubed that I was multiplying in, but also this y, and y squared became y cubed. So there we go. We have now multiplied this monomial by the trinomial in question, and that was the result. Great, so we can multiply a monomial by a monomial, or a monomial by a binomial, or a monomial by a trinomial, and this is how you do it. Let's move on. Let's practice multiplying a binomial by a binomial, right? So if we look down here, if I had a binomial, right, multiplied by another binomial, well, we just need to multiply every term of the first binomial by every term of the second binomial. And it just so happens that there's a great method for getting that done. So here's a how-to step process to multiply binomials together. Step 1 is to multiply the first terms together. Step 2, multiply the outer terms. Step 3, multiply the inner terms. And step 4, multiply the last terms together. Once you're done multiplying all of those terms together, step 5 is to combine any like terms when possible. So let me describe that a little better. First of all, when we lay it out like this, there becomes an acronym that appears, and that acronym is called FOIL, which stands for first, outer, inner, last, right? So when we follow this 4-step process here, not worrying about step 5, we're just using the first, outer, inner, last, and the acronym for that is called foiling. Okay, and so what I do is I take the first terms and I multiply them together, A times C, and I get that. That's the first terms multiplied together. And now I add that with the outer terms multiplied together of the binomial, so A times D. Those are the outer terms, the ones furthest away from each other. Okay, so that's the O. Now inner terms are the ones that are closest to each other. This B times C, those are the inner terms. And then last terms are B times D. Those are the last terms of the binomial multiplied together. Okay, and we're simply putting addition between all of those products. Or in the case of something that's negative, we would have a minus sign. So let's go ahead and practice this method of multiplying two binomials together. And so we'll look at a variety of examples here. Here's example 5.27. So when I see y plus 5 times y plus 8, I know this is multiplication because there's no operation shown between the binomials. If this was addition, I'd have a plus sign. If it was subtraction, a minus sign, or division. No, this is none of those. When there's no symbol, that implies multiplication in algebra, okay? So this is y plus 5 times y plus 8. Let's multiply the first terms together. So y times y is what we're going to multiply together, and we get y squared. And now let's multiply the outer terms together. Y times 8, that gives me an 8y. And it's positive, so I put a plus. Now the inner terms, the ones closest together, 5 times y, and that's positive. Both of those values were positive values, so I put 5y. And now the last terms get multiplied together, 5 times 8, and we get a positive 40. Now, why is my result positive for all of these? Because there were no negative values that I was multiplying. This was positive y, positive 5, positive y, positive 8. Okay, now the very last thing to do that we talked about in our process, step 5, is to combine like terms when possible. Like terms have the same variable with the same power. Now, looking at this, I see an 8y and a 5y. This is the same variable with the same power. These are like terms. Now, this is not a like term with it because the variable is raised to the second power in this case, whereas these cases, the variable was raised to the first power, but first powers are invisible. So y squared plus 13y plus 40 is my final result because I have added 8y plus 5y to get 13y. So when I multiply a binomial times a binomial, my result is a trinomial here in this case. So I got a trinomial that's three terms that are separated by addition and subtraction. In this case, addition. Let's go ahead and try this again, a little bit maybe faster. Here I go. So when I encounter this binomial times this binomial, I take 4y times 2y. And 4 times 2 is 8, and y times y is y squared. So my result is 8y squared. Now I look at my outer terms, 4y times negative 5. Those are my outer terms, and that gives me a negative 20y. And now I look at the inner terms and I multiply them together. Positive 3 times 2y, that's a positive 6y. And now I take my last terms and I multiply them together. They're constants. 3 times negative 5, that gives me negative 15. Now I look for any like terms, and you start to realize something that ends up happening. The outer and inner terms of foiling, they can be combined together. They'll usually be like terms. So negative 20y plus 6y gives me a negative 14y. And now I have, lastly, a minus 15 there. Okay, so I have combined like terms. I've ended up with a trinomial, 8y squared minus 14y minus 15. Great. We should try this a little bit more. So I'm going to give you some more examples of multiplying two binomials together. Here's example 5.28, and I see y minus 7 times y plus 4, and I immediately multiply the first terms together. Y times y is y squared. And now the outer terms, y times 4 is plus 4y. Now the inner terms, negative 7 times y gives me negative 7y. And the last terms, negative 7 times positive 4 is negative 28. Now combine any like terms, and we're done. Let's try it again. When I see 4x plus 3 times 2x minus 5, I multiply 4x times 2x to get 8x squared. I multiply 4x times negative 5 to get negative 20x. I multiply 3 times 2x to get positive 6x. And I multiply 3 times negative 5 to get negative 15. Now, all I do is combine like terms, and I notice something. Wait, this is the same thing as the previous problem. Look at this. Except instead of using the variable y, the variable x is being used. And that makes sense. This is the same thing as this, but instead of using the variable y, we're just using the variable x. So variables, it doesn't matter what variable you use, you work out the problem the same way. Now, let's go ahead and look at some more complicated binomials being multiplied together. And so here I have n squared plus 4, that's the first binomial, multiplied by n minus 1. We're going to use the same foiling. All right, so everything's the same. N squared times n is n cubed. Let me help you with that. That's n to the second power times n to the first power. I can multiply or add their exponents together in this case, right? When I'm multiplying n squared times n, I add the exponents together, and that's why I'm writing n cubed. Okay, so I've multiplied the first terms together. Let's multiply the outer terms together. That's negative 1 times n squared, so negative n squared. And the inner terms is a positive 4n. And the last terms, well, 4 times negative 1 is negative 4. And I ask myself, can I combine any like terms in this case? Are there any like terms? Like terms have the same variable with the same power. And I look at the powers of n, 3, 2, 1, and no n's. None of these are like terms, and therefore I cannot combine anything at this point. I'm done. Well, in this case here, I see two variables included in a single term, right? So p is multiplied with q, and so this is interesting. Let's go ahead and start multiplying the pieces together. So I see first terms are this and this. Well, multiply 3 times 6 and p times p and q times q. And you will get 3 times 6 is 18, p times p is p squared, and q times q is q squared. So this is the result of multiplying the first terms together. Now let's take the outer terms and multiply them together. Well, 3 times negative 11 is negative 33, and I still have that p and q. And now looking at the inner terms, 6 times 5 is 30, so I'll have a positive 30 pq. And then last terms, 5 times negative 11 is negative 55. Now I'm going to combine any like terms, which I notice that the outer and inner terms end up being like terms in this case. They both have a p and a q. Same variables with the same powers. They can be combined. So I have a negative 3pq, right? Because negative 33 plus 30 is negative 3. And then I still have that minus 55 constant at the end there. And we are done. Foiling. Great. So all of these examples that we have looked at are all just multiplying binomials together. And sometimes things get a little more complicated. Like maybe you have two variables instead of just one variable. But it's the same exact process. Okay, and here was the kind of general statement of how it works. Let's move forward. Well, if we can multiply binomials with binomials, could we multiply a binomial with a trinomial? The answer is yes. So in this next section, we're just going to take any polynomial and multiply it with another polynomial that is, we could have any situation. We should probably practice a binomial being multiplied by a trinomial. That's a great thing to practice. Or in this case, a trinomial being multiplied by a binomial, like the other way around. So let's go ahead and jump in. Now, when you multiply polynomials together, really the only thing that we're trying to do is take every term of the first polynomial and multiply it with every term of the second polynomial, right? So just make sure that you hit every single one of them, okay? So here I'm demonstrating visually what I'm about to do. Okay, so I'm taking x and I'm multiplying it with every term here, and then I'm taking 2 and I'm going to multiply it with every term here. And the amount of terms that I end up with is, just 2 times 3. So if I have a binomial times a trinomial, 2 terms times 3 terms will give me 6 terms that I end up with. And then I'll just combine any like terms if possible. So let me start. I'm going to multiply x times x squared, and that will give me x cubed. There's my first term. Now x times negative 4x, that's negative 4x squared. Now x times positive 3, that's a positive 3x. Now I move on to this term, 2. It's positive 2. So positive 2 times x squared, well, that's a positive 2x squared. And now positive 2 times negative 4x, that's a negative 8x. And positive 2 times positive 3, that's a positive 6. There we go. So I have just laid out all 6 of the terms that result in me multiplying this binomial by this trinomial. So in the end, your only objective is to multiply every term of the first polynomial with every term of the second polynomial, and you'll get the result. Now, there are like terms in this case, right? So I see a negative 4x squared and a positive 2x squared. Those are like terms because they have the same variable with the same power. And I see a positive 3x and a negative 8x. Those are like terms as well. So let's combine them. First, I have the x cubed term. You'll see the only term that had x cubed was this one, so there are no like terms with it. But negative 4x squared plus 2x squared gives me a negative 2x squared. And now positive 3x and negative 8x, well, that gives me a negative 5x. And then the only constant is here, this positive 6. So I put the positive 6 at the end, and I have now written my final result of multiplying this binomial by this trinomial. Here it is. Great. Let's go ahead and try example 5.31, which is again taking a trinomial and multiplying it by a binomial. Now, you could think of going backwards with this. Since the binomial is on the right side, you could think, oh, well, I could just multiply x into all 3 of these terms here. So it hits all 3 of them. And then this negative 3, you could multiply it into all 3 of these terms here. And then you would have hit everything. You'll have 6 terms that result. Because once again, 3 terms times 2 terms will give you 6 terms. Okay, so here I go, x times 2x squared. That gives me a 2x cubed. And x times negative 3x is a negative 3x squared. And x times 5 is a 5x. Okay, so I've just multiplied this x with all 3 of these terms. Now I'm going to multiply negative 3 into all 3 of these terms, and I get a negative 6x squared and a positive 9x and a negative 15. Okay, so negative 3 times 2x squared is negative 6x squared. Negative 3 times negative 3x is a positive 9x. And negative 3 times positive 5 is negative 15. So you see the 6 terms that result. And let's see if there are any like terms. This is the only term that has x cubed, right, where the power of the variable is 3. So I'm going to just rewrite that. Now moving on to the next terms that are x squared terms, I see a negative 3x squared and a negative 6x squared, and so that gives us a negative 9x squared as a result. And then these are like terms, this 5x and this 9x, right? They're both positive, and so when I add them together, that gives me 14x. And now I have the constant remaining here. This is the constant. It doesn't have a variable x with it. So I just tag it on to the end, and I now have this nicely created result. Okay, and one thing about when you write your results and when you think about polynomials, we like to put polynomials in a standard form where we go from the highest power of the variable and we reduce it little by little. Recall the degree of a polynomial is the highest power of the variable. We like that to go first, and then we reduce it to 2, and then x to the first, right? This is x cubed, x squared, x to the first, and then constant, which is technically x to the 0. All right? And so this is the order with which a polynomial should be written as a final result. It's organized and it helps us see key details that are important as we then address future things about polynomials. Okay, there we go. So from here, our goal is to show you some special products, some special cases when we multiply polynomials together. And so let's discuss a couple special products of multiplying polynomials. Now, there's something called a perfect square trinomial, and that's a trinomial that is the square of a binomial. Let's describe it a little bit for you. If I have just this a plus b, this is a binomial, right? A plus b, and it's squared. Then it's going to multiply out to a squared plus 2 times a times b plus b squared. Okay, so here is a binomial squared, and when we expand it, we end up writing a squared plus 2 times a times b plus b squared. All right, that's what the result is. Okay, and then like this, we could also have, instead of addition between these two terms a and b, we could have subtraction between these two terms a and b. So if I see a minus b squared, well, I can write that as this trinomial a squared minus 2 times a times b plus b squared. And this is a pattern that will come up over and over again through the rest of this course and through courses of algebra beyond this course. Let me get you comfortable with it. Okay, so let's use these patterns in example 5.32. And by the way, just a quick side note, squaring something is multiplying that thing by itself. That's the definition of squaring something. So when I see a plus b squared, I could write that as a plus b times itself. And if I was to FOIL this, right, first term's a times a squared. And then a times b, and then b times a, that gives me 2ab. And then b times b is b squared. So if you ever had a question about how to get this result from this, you could just say, well, a plus b squared is a plus b times itself. And now FOIL it, and you got that. Same thing here. This a minus b squared is a minus b times a minus b. And so if I FOIL this, right, a times a is a squared, a times negative b, and negative b times a is negative 2ab, and then negative b times negative b is positive b squared. So if you simply FOIL this, you'll do great. So let's look at example 5.32. And if I see 3x plus 5 squared, I could immediately turn that into 3x plus 5 times itself. And I can FOIL that. 3x times 3x is 9x squared. 3x times 5 is positive 15x. 5 times 3x is positive 15x. And 5 times 5 is 25. And if I combine like terms, let's say something out loud here. This is 15x plus 15x. This is just the same thing added together. Okay? So that's 2 times 15x. 2 times 15x. And so I get 30x and then the plus 25. There's my result. Now it just so happens that if I followed this just formula without foiling, I could take a and square it. Well, what is a? 3x. 3x, if I square that, that gives me 9x squared, because 3 squared is 9, x squared is x squared. Now I have this plus 2 times a times b. Well, I could take a times b. Well, that's 3x times 5, which gives me 15x. But then multiply that by 2, because there are two of them, and we get the 30x. And then 5 times 5 is b squared. That's the b squared part. If b is 5, square that. 5 times 5 is 25. So you could think of it by foiling, which I did here, or you could think of it by using this pattern. Either way. Let's try another one. When I see 4x minus 3y squared, I could do the foiling method. 4x minus 3y times itself. All right, now I'm going to multiply 4x times 4x and get 16x squared. 4x times negative 3y, which is negative 12xy. Negative 3y times 4x, which is negative 12xy. And negative 3y times negative 3y, which is positive 9y squared. So here's my result. And it just so happens that it follows this pattern that we just talked about here. Okay, this subtraction version, right? Because we had subtraction there. And so technically, if I just looked at whatever a was, 4x, and I multiplied it by itself, I squared it, then I'd get 16x squared. And then if I take a times b, right, which is 4x times 3y, well, I'd get a 12xy, but it was a minus sign between, so that's negative. And then the outer and inner terms are the same, so that's two of them. Okay? And now I take the b value, negative 3y, and I multiply it by itself, and I get positive 9y squared. So that's just following this pattern. You see similarities as we do this. And now let's combine like terms. Right? And we're done. Great. So there is a perfect square trinomial pattern that we will see over and over again as we proceed in this course. Next, let's talk about conjugates. Conjugates, here's a definition: a pair of binomials that differ only in the sign between their two terms. So if one binomial is a plus b, its conjugate is a minus b. And vice versa. Like if I had a binomial a minus b, its conjugate is a plus b. That's what vice versa means, right? We can think about it backwards. So conjugates will continue to come up over and over again in this course. And you just have to think it's the same two terms, okay, with opposite signs. This is a plus sign between the two terms. This is a minus sign between those two terms. So these binomials are called conjugates. Now, the reason why we're talking about conjugates now is because we're going to learn a new pattern called the difference of squares pattern. Okay? So if I had the difference, which is subtraction, of two things that are squared, right? Two terms that are squared, well, its factored version is the conjugates of a and b, the bases, right? A plus b times a minus b. So if I FOIL this, I would end up with this. Okay, this is called the difference of squares. You are going to need the difference of squares as you proceed in algebra because it comes up so often. Let me show you how I would multiply two conjugates together. Okay, and it's the same foiling pattern that you're used to, but something interesting is always going to happen when we multiply conjugates together. So if I see x plus 5 times x minus 5, I see these are conjugates. X and 5, plus between and minus between. So I start foiling. X times x is x squared. X times negative 5 is negative 5x. Positive 5 times x is positive 5x, and positive 5 times negative 5 is negative 25. Okay? And so what happens is the outer and inner terms of foiling end up being opposite signs of the same value. Like negative 5x plus 5x, those cancel because they're opposite signs of the same value. And what we end up with is x squared minus 25. Okay? So if instead of foiling, you wanted to recognize this pattern, that these are conjugates being multiplied together, then you would realize, hey, I could just take x and square it and subtract 5 squared, which is 25. Okay, so that's the pattern. I could take x and square it and subtract 5 and square it, and that would be the result. And with conjugates being multiplied together, the outer and inner terms always cancel each other. Let's look at another example. When I see t minus 12 times t plus 12, and if I FOIL it, t times t is t squared, t times 12 is 12t, negative 12 times t is negative 12t, and then negative 12 times positive 12 is negative 144. And once again, we notice the outer and inner terms are same value with the opposite sign, so they end up canceling each other, and we get t squared minus 144, which is exactly what we would expect from this definition here, this factoring pattern. So I have, t plus 12 times t minus 12. That's just t squared minus 12 squared. T squared minus 12 squared. Done. Let's try doing this again, maybe increasing the complexity a little bit. Okay? So when I see 2x plus 9 times 2x minus 9, technically, I could go straight to the end here and just say, well, that's going to be 2x times 2x, which is 4x squared, minus 9 times 9, which is 81. So I know my final result is going to be 4x squared minus 81 because I know that the outer and inner terms of foiling will cancel. But really fast, let's FOIL this to show. 2x times 2x is 4x squared. 2x times negative 9 is negative 18x. 9 times 2x is positive 18x. And then 9 times negative 9 is negative 81. And we see, once again, the outer and inner terms are opposite signs of the same value. And we're left with the 4x squared and the negative 81. Okay. What if we increase some of the complexity to have a power? Okay, let's go ahead and try this. We notice, hey, these are the same two terms, 5m to the fourth and n squared, 5m to the fourth and n squared, and we see addition and subtraction, so opposite signs between the terms of the two binomials. These are conjugates. All these cases, we are multiplying conjugates together. And 5m times 5m, 5m to the fourth times 5m to the fourth is 25m to the eighth. And 5m to the fourth times negative n squared is negative 5m to the fourth n squared. And now the inner terms, n squared times 5m to the fourth is also 5m to the fourth times n squared. And lastly, we have n squared times negative n squared, which is negative n to the fourth. And we notice that the outer and inner terms are the same value, opposite signs, so they cancel each other. And this becomes 25m to the eighth minus n to the fourth. That's the result. And if I wanted to, once again, I'm just going to kind of zoom in on this. We can just take this value and square it, right? And 5 squared is 25, and m to the fourth squared is m to the eighth, and then subtract b squared. The second term squared. So n squared squared is n to the fourth. Great. The last objective that we have today is multiplying polynomial functions. So if we have two functions, like f of x and g of x, if I multiply these two functions together, we can write the notation like this, f times g of x. So f times g of x is the notation. That's the same thing as taking the f of x function and multiplying by the g of x function. And if f of x and g of x are both polynomials, it's just multiplying two polynomials together. So let me show you. Okay, example 5.35 for functions f of x equals x plus 2 and g of x equals x squared minus 3x minus 4. Find f times g of x. Sure. So that's just f of x times g of x. But f of x is defined as x plus 2. That's what f of x is. So I take x plus 2, the f of x stuff, and I multiply it by the g of x stuff, which is this trinomial x squared minus 3x minus 4. Okay, so in the end, all this is really telling me to do is multiply this binomial by this trinomial, which we already did up here. We were practicing that. Okay, so let's try that one last time. It'll go really fast. And you'll recall we need to multiply every term of one polynomial with every term of the other polynomial. And so x times x squared gives me x cubed, and x times negative 3x gives me negative 3x squared, and x times negative 4 gives me negative 4x, and 2 times x squared is 2x squared, and 2 times negative 3x is negative 6x, and 2 times negative 4 is negative 8. Okay. Now, we can combine any like terms. So I see x cubed is this is the only term with power of 3. Now I'm going to look at my x squared terms, like here I have negative 3x squared and positive 2x squared, which gives me negative 1x squared, so I write that. And now I have a negative 4x and a negative 6x, which combine together to make negative 10x. And then lastly, I have this constant negative 8, and so I write the negative 8 at the end. So here is the result of multiplying these two functions together. So I had two functions that I multiplied together. Those two functions were x plus 2 and x squared minus 3x minus 4. And I did that multiplication, and I ended up with 6 terms, right? Because 2 terms times 3 terms is 6 terms. And this is my simplification. Now, for this next part, this last little bit, it asked me to find f times g of 2. So it wants me to input 2 into the functions. Now, you could do this in a more complicated way by taking this 2 input and inputting it into the f of x function, and then inputting it into the g of x function, and then multiplying your outputs together, right? Multiplying the f of x output with the g of x output. Or you can be more clever. Here's what clever students do. Well, they already found f times g of x. It's this stuff. So they can input 2 in for x in this answer that we got here. So this is f times g of x. I want to find f times g of 2. Just input 2 in for x in this expression. So that's what I'll do. I'm going to take 2 and cube it, and subtract 2 squared, and subtract 10 times 2, and then subtract 8. And 2 cubed is 8, minus 2 squared, which is minus 4, minus 10 times 2, which is minus 20, and then the minus 8 constant at the end. And you'll notice I have 8 minus 8, which cancels, and negative 4 minus 20 is negative 24. I have just found out that f times g of 2 is negative 24. I simply took the input of 2, and I plugged it in right there, boom, 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 and I got my output. Thank you. I hope you have a wonderful day, Thank you for learning how to multiply polynomials with me.